The universe is an endless tapestry of wonders, a place where the laws of physics twist and bend in ways that defy logic. Out there, in the infinite black, lurk cosmic anomalies, phenomena so bizarre, so utterly perplexing, that even the brightest minds struggle to unravel their secrets. Picture a black hole so massive it warps space-time itself, or a star that vanishes without a trace. These aren't scenes from science fiction. They're real mysteries written in the fabric of the cosmos, waiting to be decoded. And today, we're diving deep into 25 of the most astonishing cosmic anomalies ever discovered, phenomena that challenge everything we think we know about the universe. Imagine gazing up at the night sky where every flickering light holds a story. Some of those stories are straightforward, a star burning bright, a planet orbiting its sun. But others, they're riddles wrapped in enigmas. Take, for instance, the eerie radio signals pulsing from deep space, repeating in patterns we can't explain. Or the colossal void spanning billions of light years, a place where galaxies simply don't exist. These aren't just quirks of nature, they're cosmic puzzles that force us to question the very foundations of reality. What if the universe is hiding something far stranger than we've ever dared to imagine? This journey isn't just about listing oddities, it's about stepping into the unknown, where each anomaly is a breadcrumb leading us closer to the truth. Some of these mysteries might hold the key to unlocking new physics, while others could rewrite our understanding of time, space, and existence itself. From inexplicable fast radio bursts to ancient celestial structures that shouldn't exist, we're about to explore the edges of human knowledge, so buckle up. By the time we're done, you'll see the universe not as a cold, empty void, but as a living, breathing mystery, teeming with secrets just waiting to be uncovered. The cosmos has been keeping its strangest stories hidden until now. Among all the strange signals ever detected from deep space, none has sparked more fascination or controversy than the WOW signal. It was the evening of August 15, 1977, when a radio telescope at Ohio State University known as the Big Ear picked up something extraordinary. A burst of radio waves 72 seconds long, so powerful and so unusual that astronomer Jerry Amon circled the data on the printout and scribbled a single word in the margin: "Wow." The signal wasn't just strong, it was eerily precise. It came from a region near the constellation Sagittarius, and it matched the exact frequency scientists had predicted an intelligent civilization might use to broadcast its presence: 1420 megahertz, a quiet spot in the radio spectrum where natural cosmic noise is minimal. For decades, researchers have combed the same patch of sky, listening for a repeat, but the signal never returned. So what was it? Some believe it could have been a message from an advanced extraterrestrial civilization, a fleeting hello from a distant star. Others argue it was something far more mundane, perhaps a passing comet emitting radio waves, or even a reflected transmission from a human-made satellite. But none of these explanations quite fit. The signal's intensity, its narrow frequency range, and its sudden appearance and disappearance remain unmatched by any known natural phenomenon. The WOW signal stands as one of the greatest unsolved mysteries in the search for extraterrestrial intelligence. It's a ghost in the cosmos, a whisper from the void that raises more questions than answers. If it was artificial, who or what sent it? And if it wasn't, why have we never detected anything like it since? Decades later, that lone burst of radio noise still taunts us, a cosmic riddle written in a language we don't yet understand. While humanity races to launch satellites into orbit, some believe we may have been beaten to the punch. By thousands of years, enter one of space's most enduring urban legends, the Black Knight satellite. Stories whisper of a mysterious object silently circling our planet, its origins lost to time. Ancient alien theorists claim it's been orbiting Earth for 13,000 years, an artificial watcher from the stars. But where does myth end and reality begin? The legend first took flight in 1960 when newspapers reported that the U.S. Navy had detected a dark, unidentified satellite orbiting Earth, something no nation had launched. Even stranger, amateur radio operators had been picking up odd delayed echoes of their own signals since the 1920s, as if something unknown in space was bouncing them back. Then came the grainy photographs, shadowy, irregular shapes captured during early space missions, including one from the 1998 Space Shuttle Endeavour that showed an angular silhouette against Earth's curve. Scientists have explanations. The satellite sightings likely stem from thermal blankets lost during spacewalks, or debris like the remnants of old spacecraft. Those eerie radio echoes, they're probably caused by charged plasma in Earth's ionosphere. But here's where things get interesting, because not every Black Knight claim has been fully debunked. Classified military satellites do exist, and some space debris behaves unpredictably, tumbling in ways that defy easy identification. Could there be a kernel of truth buried beneath the layers of speculation? In 2015, astronauts aboard the International Space Station filmed something unusual. A dark object drifting past at high speed, its origins never confirmed. And while the Black Knight almost certainly isn't an alien artifact, its legend endures because it taps into a deeper question. If humanity only started exploring space less than a century ago, how can we be certain we're truly alone in Earth's orbit? Sometimes the most compelling mysteries aren't about what we find, but what we might have missed. Deep in the cosmos, something strange is tugging at entire galaxy clusters, not just moving them, but pulling them in the same direction at staggering speeds. Scientists call this enigma dark flow, and it's as unsettling as it sounds. Picture hundreds of massive galaxy clusters, each weighing trillions of suns, all streaming toward a single point in space like cosmic rivers drawn by an invisible current. The problem: there's nothing there, no supermassive structure, no known force powerful enough to explain their synchronized motion. This isn't just a puzzle, it's a direct challenge to our understanding of how the universe works. The discovery came from meticulous observations of galaxy clusters using the Wilkinson Microwave Anisotropy Probe and later the Planck satellite. By studying the way hot gas within these clusters scattered cosmic microwave background radiation, the faint afterglow of the Big Bang, researchers noticed something bizarre. The clusters weren't just drifting randomly, they were racing toward a patch of sky near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. And here's what defies logic: the pull isn't coming from anything we can see. The observable universe, with all its galaxies and dark matter, shouldn't have a structure massive enough to cause this motion. So what's behind dark flow? One radical theory suggests the gravitational influence of something outside our observable universe, perhaps another universe brushing against ours in the vast multiverse. It's like feeling a breeze from a door we can't see, hinting at realms beyond our cosmic horizon. Other scientists propose flaws in our measurements or unseen extensions of known superclusters, though none fully account for the scale of this motion. The most unsettling possibility: that dark flow reveals a fundamental gap in our grasp of gravity itself, a shadow where the rules we've trusted might crumble. Every clue deepens the mystery. In 2018, studies found the flow extends even farther than initially thought, billions of light years beyond the clusters first observed. If confirmed, this would mean whatever's pulling them isn't just hidden, it's titanic, dwarfing anything in recorded existence. Yet without a visible source, dark flow remains a ghost in the data, a cosmic whisper that something, or somewhere out there, is rewriting the script of the universe. For now, it stands as a humbling reminder: the more we map the cosmos, the more it surprises us with motions we can't yet explain. We've scoured the cosmos for signs of alien civilizations, built telescopes powerful enough to peer across billions of light years, and yet silence. This unsettling contradiction has a name, the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It highlights the jarring mismatch between our expectations and reality. The numbers tell us the universe should be teeming with life, with hundreds of billions of galaxies, each containing billions of stars and countless planets. The odds seem overwhelming. So why does the cosmos feel so empty? One chilling possibility is the Great Filter, a hypothetical barrier that prevents life from advancing beyond a certain point. Maybe the filter lies in our past, something so rare about Earth's conditions that complex life is virtually impossible elsewhere. Or worse, it could wait ahead of us, a catastrophic event that inevitably wipes out civilizations before they can spread across the stars. Nuclear war, environmental collapse, or even self-replicating nanobots could be cosmic dead ends we haven't encountered yet. The terrifying implication. If the Great Filter is still ahead of us, humanity might be marching toward its own expiration date without realizing it. Others suggest less ominous explanations. The zoo hypothesis proposes that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a wildlife preserve. They might be observing us silently, waiting for humanity to reach a certain level of maturity before making their presence known. Or consider the idea that aliens communicate in ways we can't yet perceive using neutrino beams or quantum entanglement. Technologies so advanced they're indistinguishable from magic to our current understanding. Then there's the sheer scale of time and space to reckon with. Civilizations might rise and fall in cosmic blinks, their signals fading before we ever detect them. Imagine two fireflies in a vast forest, flashing their lights at random moments, never overlapping long enough to notice one another. That could be humanity's place in the universe, not alone, just tragically out of sync. Perhaps the most humbling answer is that we're simply looking for the wrong things. Our searches focus on radio waves and laser pulses, but what if advanced societies abandoned those technologies millennia ago? They might have moved beyond physical forms, existing as digital consciousness or harnessing dark energy in ways we can't fathom. The Fermi Paradox isn't just a question about aliens, it's a mirror forcing us to confront how little we truly understand about life, intelligence, and our own future in this vast, whispering cosmos. Hidden behind a cosmic curtain of dust and stars, an invisible behemoth is pulling hundreds of galaxies, including our own Milky Way, toward it at breathtaking speeds. This is the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxies like a celestial puppeteer. Picture a river wider than the observable universe, with galaxies as leaves caught in its current, all flowing toward a point we can't even see. The mystery, it lies directly behind the Milky Way's crowded disk, buried in what astronomers call the zone of avoidance. A region so dense with gas, dust, and blinding starlight that our telescopes struggle to pierce through. Discovering the Great Attractor was like realizing the ground beneath your feet is slowly tilting. In the 1970s, astronomers noticed something odd. Galaxies in our local supercluster weren't just drifting apart due to the universe's expansion. Instead, they were all sliding sideways as if dragged by an unseen hand. Further studies revealed the culprit, a gravitational force equivalent to tens of thousands of Milky Ways, concentrated in a spot 250 million light-years away. But when researchers pointed their instruments in that direction, they hit a wall. The zone of avoidance blocked their view like a cosmic blindfold, leaving them to map the unseen using radio waves and X-rays that could penetrate the dust. What could possibly wield such force? Early theories suggested a massive cluster of galaxies, but the numbers didn't add up. Then came a revelation. The Great Attractor might just be the tip of something far larger. Observations revealed that our galaxy's motion doesn't stop there. We're being pulled toward an even more enormous structure called the Shapley supercluster, a sprawling metropolis of galaxies over 600 million light-years away. Some scientists now believe the Great Attractor is merely a waypoint in this grand cosmic migration, a stepping stone in a flow of matter stretching across the universe. Yet the most intriguing possibility remains. Could the Great Attractor be something stranger, and not in space-time, a remnant of the early universe's chaotic inflation, or even a gravitational echo from another dimension? Every breakthrough peels back another layer, but the core of the mystery persists. As new telescopes peer through the zone of avoidance with infrared and radio eyes, we edge closer to answers. But for now, the Great Attractor stands as both a landmark and a riddle, a reminder that the universe's most powerful forces often hide in plain sight just beyond our gaze. Some stars flicker gently like candles in the wind, but one star in the constellation Cygnus doesn't play by those rules. KIC 8462852, better known as Tabby's star, behaves like nothing else in the cosmos. Most stars dim predictably when planets pass in front of them, casting tidy, symmetrical shadows. But Tabby's star doesn't just dim, it plummets, dropping in brightness by up to 22% in chaotic, irregular dips that can last for days or even weeks. These aren't the clean signals of orbiting worlds. They're more like something massive, jagged, and utterly unnatural passing between us and the star. The mystery began in 2015 when citizen scientists poring over data from NASA's Kepler spacecraft flagged the star's bizarre light patterns. At first, astronomers scrambled for conventional explanations. Could it be a swarm of comets, thousands of them, trailing enough dust to blot out a fifth of the star's light? Maybe, but no comet field we've ever seen behaves like this. Others suggested a recent planetary collision, with debris still lingering in orbit. But the star's light also shows a long-term dimming trend, fading by nearly 3% over the past century. That's not just odd, it's unprecedented for a star of its type. Then came the theory that set the internet ablaze: alien megastructures, specifically a Dyson swarm hypothetical energy collecting constructs built by an advanced civilization to harness their star's power. The idea isn't as far-fetched as it sounds. In 1960, physicist Freeman Dyson proposed that a sufficiently advanced society might encase its star in solar panels, creating signatures just like Tabby's erratic dimming. Suddenly, astronomers weren't just studying a star, they were confronting the possibility of humanity's first hard evidence of extraterrestrial engineering. But science demands more than excitement, it demands proof. Subsequent studies revealed that the dimming isn't uniform across all wavelengths, as you'd expect from solid megastructures. Instead, it's patchy, suggesting fine dust particles are the more likely culprit. Yet even this explanation leaves gaping holes. Dust should be blown away by stellar radiation over time, so why does the dimming persist? And why does it happen in such irregular, dramatic bursts? Tabby's star refuses to fit neatly into any box we try to put it in. It's not behaving like a young star with a debris disk, nor like an old star with planets. It's an outlier, a cosmic rebel that dares us to rethink what we know about stellar evolution. Every new observation adds another twist, like the discovery that the star's dimming events seem to cluster in strange, non-random patterns, almost as if something out there is following a rhythm we can't yet decipher. For now, Tabby's star remains an enigma, its secrets locked behind a veil of dust or something far more extraordinary. It's a reminder that the universe doesn't owe us tidy answers. Sometimes the most profound discoveries begin with a single, stubborn anomaly that won't behave. And until we solve this puzzle, Tabby's star will keep us guessing, one erratic flicker at a time. If the cosmos had a heartbeat, it might sound something like fast radio bursts, blindingly intense pulses of radio waves that flash across the universe in less time than it takes to blink. First detected in 2007, these bursts pack more energy than the sun emits in 80 years into mere milliseconds, vanishing before astronomers can even turn their telescopes toward the source. What makes them truly baffling isn't just their power, but their impossible origins. They're coming from galaxies billions of light years away, flung across the void by forces we're only beginning to comprehend. The mystery deepens with the outliers, the repeaters. Most FRBs are one-offs, celestial lightning strikes that never recur, but a handful, like FRB 121102, pulse erratically, flickering on and off like a cosmic Morse code no one can decipher. In 2020, scientists traced one repeating burst to a surprising culprit, a magnetar, a highly magnetic neutron star in our own Milky Way. For a moment, it seemed the puzzle was solved, until deeper analysis revealed most FRBs come from far beyond our galaxy, and their energies dwarf anything a magnetar should produce. So what's really behind these cosmic fireworks? Theories range from the plausible to the extraordinary. Colliding neutron stars or evaporating black holes could generate such bursts, but their irregular patterns don't always fit. Some speculate they're the death throes of advanced civilizations. Imagine a power source so vast it briefly outshines galaxies, or propulsion beams from alien starships punching through space-time. Others suggest they're natural yet undiscovered phenomena, like cosmic strings vibrating or quantum fluctuations in the fabric of space itself. The challenge lies in catching them. FRBs are fleeting, often vanishing before their precise location can be pinpointed. New telescopes like CHIME in Canada are revolutionizing the hunt, detecting dozens per month, yet each discovery brings fresh contradictions. Some bursts are polarized, twisted by magnetic fields in ways we can't yet explain. Others arrive with a lower frequency afterglow, hinting at complex physics unfolding in their wake. Perhaps the most tantalizing clue lies in their distribution. FRBs seem sprinkled randomly across the sky, with no preference for galaxies rich in stars or dust. If they were strictly natural, we'd expect patterns concentrations near dense stellar nurseries or ancient elliptical galaxies. Their randomness keeps even the boldest theorists guessing. These bursts are more than cosmic oddities, they're messengers. Each one carries imprints of the gas and plasma it's traversed, offering a roadmap to the universe's hidden structure. By studying their distortions, we're uncovering invisible matter woven between galaxies, threads of the cosmic web we'd never see otherwise. Yet for all their scientific value, FRBs remain fundamentally enigmatic, a reminder that the universe still holds phenomena so wild, they defy even our most imaginative explanations. Every millisecond burst is a question etched in radio waves, waiting for us to decode its secrets. In the vast ocean of galaxies, where clusters and superclusters form glittering metropolises, there exists a desert so vast it defies comprehension, the Boötes void. Stretching 330 million light-years across, this cosmic emptiness isn't just a gap. It's a staggering absence, a hole in the universe's fabric where galaxies should thrive but don't. Astronomers call it the Great Nothing, and its existence throws a wrench into everything we thought we knew about how matter organizes itself in the cosmos. Imagine standing in the middle of a football stadium packed with cheering fans, only to realize one entire section of seats is eerily vacant. That's the Boötes void on a galactic scale. While typical voids between galaxy clusters span tens of millions of light-years, this one dwarfs them all. Discovered in the 1980s during surveys of galaxy distributions, it holds only 60 galaxies where thousands should exist. To put that in perspective, if the Milky Way were a grain of sand, the Boötes void would be an empty swimming pool with just a few scattered grains tossed in. How does something this empty form? One leading theory suggests it's the ghostly imprint of an ancient collision between bubble-like regions of space-time during the universe's inflationary period, leaving behind a literal cosmic dead zone. Others propose it's the result of dark energies accelerating expansion, stretching matter so thin that galaxies never had a chance to clump together. But even these explanations fall short. The void's sheer size and razor-sharp edges don't match simulations of cosmic evolution. It's as if someone took an eraser to a quarter of the observable universe and scrubbed away the galaxies. The strangest part, the galaxies that do exist within the void aren't normal. They're isolated, outlier starships drifting in an ocean of darkness, showing signs of accelerated star formation, almost as if they're desperately trying to compensate for the emptiness around them. Some astronomers speculate these lone galaxies might be refugees, ejected from clusters by gravitational slingshots billions of years ago. Others wonder if they're evidence of an entirely unknown process, one that somehow prevents galaxies from forming in the first place. Then there's the unsettling possibility that the Boötes void isn't empty at all. Could it be filled with invisible dark matter, or even something more exotic like a relic from a collision with another universe? The void's gravitational pull suggests something massive lurks there, tugging at surrounding galaxies, but our telescopes see nothing. It's a cosmic hide-and-seek champion, refusing to reveal its secrets. For now, the Boötes void remains one of the universe's most humbling mysteries. It challenges our models, defies our expectations, and forces us to confront how little we truly understand about the large-scale structure of reality. Every telescope pointed toward it brings back the same eerie message. Sometimes the most profound cosmic truths aren't written in the stars but in the silence between them. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, a visitor from another star. Named Oumuamua, a Hawaiian word meaning scout or messenger, this object was the first confirmed interstellar traveler ever detected passing through our cosmic neighborhood. But from the moment it was spotted, Oumuamua defied every expectation. It didn't move like a typical asteroid or comet. It didn't look like one either. And most baffling of all, it accelerated as it raced away from the sun, as if something unseen was pushing it. At first glance, Oumuamua seemed ordinary, a reddish, rocky object about the size of a football field. But the details quickly turned bizarre. Unlike most asteroids, which are lumpy or irregular, Oumuamua was oddly elongated, some estimates suggesting it was 10 times longer than it was wide, a cosmic cigar tumbling through space. Then came the real shock, its trajectory. After slingshotting past the sun, it sped up unexpectedly, a behavior comets usually exhibit when their ices vaporize, creating a visible tail. Yet Oumuamua had no tail, no coma, no detectable gases, nothing to explain its sudden burst of speed. Theories erupted like supernova. Could it be a hydrogen iceberg sublimating invisible gas as it warmed? Or perhaps a porous dust bunny of loosely bound particles, light enough to be nudged by sunlight itself? Harvard astrophysicist Avi Loeb proposed an even more radical idea. Oumuamua might be artificial, a solar sail or derelict probe from an alien civilization. Though controversial, the hypothesis gained traction because natural explanations kept falling short. No model perfectly accounted for its acceleration, its shape, or its eerie lack of outgassing. Then there's the mystery of its origin. Tracing its path backward suggests Oumuamua came from the general direction of Vega, though it had traveled so long, possibly hundreds of millions of years, that Vega wasn't even in that position when it began its journey. That raises another chilling possibility. Oumuamua could be a fragment from a shattered world, hurled into the void by some cataclysmic event in a distant star system. The real frustration, we'll likely never know for sure. By the time Oumuamua was detected, it was already speeding away, too faint and too fast for even our most powerful telescopes to catch more than fleeting glimpses. Future observatories like the Vera Rubin telescope may spot more interstellar objects, but Oumuamua remains our first and so far most enigmatic cosmic messenger. It's a tantalizing reminder that the universe is far stranger than we imagine, and that even the things passing right through our backyard can hold secrets we're just beginning to unravel. The universe is supposed to be indifferent, no preferred direction, no special alignment. But when scientists mapped the faint afterglow of the Big Bang, they stumbled upon something that shouldn't exist, a pattern aligned with our solar system's plane, as if the cosmos itself had tilted its head to look directly at us. They called it the axis of evil, and its existence throws into question one of the most sacred principles of cosmology, the idea that the universe is fundamentally the same in all directions. This eerie alignment was buried in the data of the cosmic microwave background, the oldest light in the universe. When researchers analyzed temperature fluctuations in this radiation, tiny variations that reveal the seeds of galaxies and galaxy clusters, they expected randomness. Instead, they found a strange correlation. Certain large-scale patterns lined up suspiciously well with the ecliptic, the plane of Earth's orbit around the Sun. It's as if the universe's blueprints were drawn with a ruler pointing straight at us, a cosmic coincidence so unlikely that it defies the Copernican principle, which states we hold no privileged place in the cosmos. The implications are staggering. If the axis of evil is real and not some statistical fluke, it could mean our understanding of inflation. The rapid expansion of the universe just after the Big Bang is fundamentally flawed. Maybe the universe isn't as uniform as we thought. Perhaps there's a hidden structure, a lopsidedness written into the fabric of space-time itself. Skeptics argue the alignment might be an illusion, a trick of measurement errors or foreground interference from dust in our own galaxy. But multiple independent studies, including data from the Planck satellite, have repeatedly detected the same unsettling pattern. Even stranger, the axis doesn't just align with our solar system, it also eerily matches the orientation of other mysterious anomalies, like the unexpected motion of galaxy clusters in the dark flow. Could these phenomena be connected? Some theorists speculate that the axis of evil hints at a pre-Big Bang universe, a shadow of some prior structure that left its imprint on our cosmic infancy. Others suggest it's evidence of a multiverse, where neighboring universes exert gravitational tugs on our own, skewing the cosmos like a ship listing in unseen currents. For now, the axis of evil remains one of cosmology's most stubborn puzzles. It mocks our assumptions, whispering that the universe might not be the impartial expanse we've always believed. With every new observation, scientists inch closer to the truth, but whether the answer will resolve the mystery or deepen it, no one can yet say. One thing's certain: if this axis is real, we're staring straight down the barrel of a cosmic enigma that could rewrite the rules of reality itself. Among the swirling chaos of cosmic gas and dust, where most nebulas twist into organic, flame-like shapes, one structure stands out like a meticulously drafted blueprint: the Red Rectangle Nebula. Situated about 2,300 light-years away in the constellation Monoceros, this celestial oddity is a perfect geometric puzzle, its four stark corners forming a near-perfect rectangle framed by glowing crimson beams that crisscross like searchlights. Most nebulas are born from the explosive deaths of stars, their debris scattered in wild, asymmetrical clouds, but the Red Rectangle, it looks as though it was engineered with a cosmic ruler, and that precision has left scientists scratching their heads for decades. At the heart of this enigma lies a dying binary star system, HD 44179, pumping out dense jets of gas and dust. Normally, such outflows create chaotic, hourglass-shaped planetary nebulas. Yet here, the expelled material aligns into crisp X-shaped spikes and a rectangular halo so symmetrical it borders on artificial. One theory suggests the star's thick dust disk acts like a stencil, funneling escaping gas into those exact right angles. But even that explanation feels incomplete. No other known nebula, even those with similar disk structures, has ever produced such razor-sharp geometry. Then there's the color. The Red Rectangle's eerie glow comes from a rare form of carbon-based molecules called polycyclic aromatic hydrocarbons, lit up by the dying star's ultraviolet radiation. But why this nebula fluoresces so intensely red, while others with similar chemistry don't, remains another unsolved piece of the puzzle. Some researchers speculate that the molecules here are aligned in an unusually ordered way, almost like a crystalline structure, amplifying the red hue in a process we've never observed elsewhere. Of course, where science falters, imagination rushes in. The nebula's unnatural symmetry has fueled whispers of extraterrestrial megastructures, perhaps an ancient Dyson sphere under construction, or even a cosmic beacon deliberately designed to catch our attention. While there's zero evidence to support these ideas, the very fact that they don't sound completely absurd speaks to how utterly unique this nebula is. Nature tends to favor curves and chaos, not right angles and precision. The red rectangle refuses to fade quietly. Recent observations reveal its central star is still actively shaping the nebula, with new jets emerging in unexpected directions. Each study peels back another layer, yet the core mystery endures. How can something so orderly emerge from the violent, turbulent death throes of a star? Until we find another example like it, and so far we haven't. This crimson geometric wonder will keep challenging our assumptions about how the universe builds its structures. Sometimes the most profound cosmic questions aren't about the vast and chaotic, but about the unnervingly perfect. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, they carried humanity's greetings to the star's gold plaques depicting our species drifting toward the infinite. But as these probes hurtled toward interstellar space, something bizarre happened. They began slowing down ever so slightly, as if an invisible hand had reached out to tug them backward. This tiny but persistent deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, and for 3 decades it haunted physicists like an unsolved equation scribbled in the margins of the universe. At first, scientists scrambled for explanations. Could it be the gravitational pull of undiscovered matter lurking in the outer solar system, the influence of dark energy making its presence known at close range? Even modifications to our understanding of gravity itself were proposed. The numbers were too precise to ignore. Both Pioneer probes, separated by vast distances, experienced nearly identical deceleration, ruling out random instrument error. Yet no known force in physics could account for it. Then came the breakthrough. Meticulous reconstructions of the probe's designs revealed an overlooked culprit: heat. The plutonium-powered radioisotope thermoelectric generators aboard both spacecraft emitted warmth, and that thermal radiation wasn't perfectly symmetrical. As photons escaped from the spacecraft surfaces, particularly the back of their parabolic antennas, they imparted a tiny but measurable push in the opposite direction, like a car slowing because someone opened a window, letting air rush out. Simulations confirmed this effect matched the anomalous deceleration almost exactly. Case closed, or so it seemed, but here's where the story twists. While thermal radiation explains most of the anomaly, some researchers argue it doesn't account for all of it. The deceleration's magnitude still shows minor discrepancies, particularly in early mission data. Could there be another layer to this mystery? A few daring theorists suggest quantum vacuum effects or even subtle space-time curvature variations near the solar system's edge might still play a role. Others counter that these are just measurement artifacts lost in noise, though no one can say for certain. The Pioneer Anomaly stands as both a triumph of scientific diligence and a humbling lesson in cosmic humility. It reminds us that even our most precise instruments operate within a universe teeming with subtle, unseen forces, and that sometimes the answers we seek are hiding in the glow of our own spacecraft, whispering from the shadows of human ingenuity. For all we've learned, the Pioneer's quiet defiance still lingers, a ghostly nudge toward the next great cosmic question waiting to be uncovered. The moon hangs in our sky like a silent sentinel, a cratered world we think we know, yet its past hides a magnetic personality we never expected. Today, the Moon's magnetic field is practically non-existent, barely a whisper compared to Earth's protective shield. But rock samples brought back by Apollo astronauts revealed something astonishing. Over 3 billion years ago, the Moon's magnetic field was up to 100 times stronger than Earth's is today. This shouldn't be possible. Magnetic fields require churning, molten metal cores, and the Moon's small size means its core should have cooled and solidified eons ago, shutting off any dynamo effect. So how did our tiny neighbor once boast a magnetic field rivaling some planets? The answer lies in a cosmic dance of forces we're only beginning to understand. One leading theory suggests the Moon's early orbit was far more dynamic than we imagined. Gravitational interactions with Earth could have stretched and squeezed its molten core like a cosmic accordion, generating turbulence intense enough to power a magnetic dynamo. Picture a child spinning a marble in a cup. The irregular motion keeps the liquid inside swirling long after it should have settled. Similarly, the Moon's wobbling rotation might have stirred its core for billions of years longer than models predict. Then there's the impact hypothesis. Ancient lunar rocks show signs of intense magnetism dating back to a time when the Moon was bombarded by massive asteroids. These collisions could have triggered colossal lava flows, temporarily reigniting convection in the core like a struck bell reverberating with energy. But even this explanation has holes. Why would such a fleeting mechanism sustain a strong field for hundreds of millions of years? The most tantalizing clue comes from tiny mineral grains in lunar samples. These crystals, magnetized like compass needles frozen in time, point to periods when the Moon's field flickered on and off unpredictably. Some scientists now suspect the Moon's dynamo didn't die gradually. It short-circuited in fits and starts, possibly due to crystallizing iron in its core creating chaotic currents. Imagine a power grid surging and failing as wires fray, and you've got a glimpse of the Moon's ancient magnetic tantrums. What makes this mystery even more profound is its implications for other worlds. If small, rocky bodies like the Moon can generate strong magnetic fields against all odds, then exoplanets we've dismissed as lifeless might harbor hidden protections against lethal cosmic radiation. The Moon's magnetic past is more than a lunar curiosity. It's a key to rewriting the rules of planetary evolution. Every new mission, every speck of lunar dust analyzed, brings us closer to understanding how something so seemingly inert once thrummed with unseen cosmic energy, defying expectations written in the stars. Stretching across the night sky like a celestial continent, the Hercules Corona Borealis Great Wall isn't just a cluster of galaxies, it's a cosmic monument, a structure so vast it strains the limits of what we thought possible. At 10 billion light-years long, this megastructure dwarfs everything else in the observable universe, a filament of galaxies and dark matter woven into a ribbon 7 times longer than the distance from Earth to the farthest visible quasars. And its very existence throws a wrench into one of cosmology's most sacred principles, the idea that, on the largest scales, the universe should look roughly the same in every direction. This titanic wall was discovered in 2013, hidden in plain sight within data from gamma-ray bursts, the most violent explosions in the universe. These bursts act like cosmic breadcrumbs, marking the locations of distant galaxies too faint to see directly. When astronomers mapped their positions, an unsettling pattern emerged, an improbable concentration of galaxies forming a near-perfect arc across the constellations Hercules and Corona Borealis. The odds of such a structure forming by random chance, less than 1 in 10,000. It's as if someone drew a line across the cosmos and said, "Build here." The cosmological principle, the bedrock of modern astronomy, insists the universe must be homogeneous at grand scales, no special places, no preferred directions. Yet the Great Wall defies this, posing a paradox. How could gravity have sculpted something so enormous in the time since the Big Bang? Current models suggest structures larger than 1.2 billion light-years shouldn't exist, gravity simply hasn't had enough time to pull matter together over greater distances. But the Great Wall laughs at these constraints, spanning nearly a tenth of the observable universe's diameter. Some theorists scramble for explanations. Could it be a fossil from the universe's inflationary epoch, a frozen ripple in space-time that seeded anomalous clustering? Others wonder if we're seeing a statistical illusion, a trick of perspective where multiple smaller structures align by chance. But the most tantalizing and unsettling possibility is that the cosmological principle itself might need revision. What if the universe isn't as uniform as we've assumed? Adding to the intrigue, the Great Wall isn't alone. It's part of a growing family of impossible megastructures like the Sloan Great Wall and the South Pole Wall, each stretching the definition of cosmic scale. Together, they hint at a universe far more textured and intricate than our models predicted, a place where matter clumps in ways we're only beginning to fathom. For now, the Hercules Corona Borealis Great Wall stands as both a marvel and a provocation, a cosmic bridge to realms we don't yet understand. It dares us to reconsider not just the universe's structure, but the very principles we've used to define it. Every new telescope trained on this galactic leviathan brings us closer to an answer, or perhaps to a deeper mystery still. In the frozen echo of the Big Bang, where the cosmic microwave background paints the universe's oldest light, there's a patch of sky that doesn't belong. Nestled in the constellation Eridanus lies a chilling anomaly, a sprawling cold spot so vast it could swallow 10,000 Milky Ways, its temperature a stark whisper below the surrounding cosmos. This is the Eridanus supervoid, a cosmic absence so profound it defies the odds, stretching 1.8 billion light-years across like a shadow cast by something we can't see. When scientists first mapped the cosmic microwave background using satellites like WMAP and Planck, they expected minor fluctuations, tiny variations in temperature telling the story of the universe's infancy. But the Eridanus cold spot stood out like a frozen thumbprint. Its temperature dipped 20 times colder than standard models predicted. At first, researchers assumed it was a glitch, an artifact of measurement noise. Yet repeated observations confirmed its reality. This wasn't an error. It was a cosmic puzzle written in negative space, the leading theory, a supervoid, an unfathomably empty region where galaxies, stars, and even dark matter are eerily scarce. In such a void, photons from the cosmic microwave background would lose energy as they traverse the expanding space, cooling slightly in a process called the integrated Sachs-Wolf effect. But here's the catch: the Eridanus cold spot is too cold, and the void required to explain it would need to be larger and emptier than any structure gravity should have allowed to form in the universe's lifetime. It's like finding a single, perfect square mile of vacuum in the middle of a bustling city. Nature doesn't work that way without a reason, of course. Alternative explanations abound. Could the cold spot be a bruise from a collision with another universe, a relic of multiverse physics imprinted on our sky? Some theorists propose it's evidence of a cosmic texture, a defect in space-time structure left over from the universe's violent birth. Others suggest it's not a void at all, but a cluster of distant galaxies whose gravitational pull distorts the microwave background in ways we don't yet understand. But every hypothesis comes with its own contradictions, leaving the cold spot suspended between theories like a question mark in the cosmos. The most tantalizing clue lies in the void's apparent emptiness. Surveys like the Dark Energy Survey have mapped galaxy distributions in the region, finding fewer galaxies than expected, but not nearly enough to account for the temperature drop. This discrepancy has led some to speculate that the supervoid might be filled with something invisible, perhaps an exotic form of dark energy or matter interacting with light in ways we can't yet detect. It's a reminder that the universe's greatest mysteries often lurk not in the light, but in the shadows we've yet to illuminate. For now, the Eridanus supervoid remains a cosmic paradox, a cold enigma that challenges our understanding of structure formation and the very nature of space itself. With every new telescope and deeper sky survey, we peel back another layer, but the heart of the mystery only grows colder. Whether it's a flaw in our models, a window into parallel realities, or something stranger still, one thing is certain: the universe has carved out a hole in the sky, and we're only beginning to fathom what it means. The universe has a habit of balancing its books except when it doesn't. According to the Big Bang's meticulous ledger, there should be a precise amount of ordinary matter, or baryons, floating around today, the protons and neutrons that make up everything from stars to human beings. But when astronomers tally up all the visible galaxies, stars, and gas clouds, they come up short, way short. Nearly half the universe's baryons are missing, as if the cosmos misplaced an entire chunk of itself. This isn't just a rounding error, it's a glaring gap in our understanding of where and how matter hides. The mystery begins with the cosmic microwave background, that ancient afterglow of the Big Bang. Its subtle temperature fluctuations act like a recipe book, telling us exactly how much ordinary matter the universe started with. Fast forward 13.8 billion years, and we'd expect to find all those baryons neatly packed into galaxies or drifting between them. Yet when we count everything we can see, stars, planets, interstellar dust, we're only accounting for about 60% of what the math says should exist. So where's the rest? Astronomers have turned their telescopes to the most barren stretches of intergalactic space, suspecting the missing matter might lurk there as diffuse, superheated gas. Imagine searching for a fog so thin it's practically invisible, spread across billions of light years. That's the challenge, but recent breakthroughs suggest they're on the right track. By studying how light from distant quasars filters through the cosmos, scientists have detected traces of this elusive material, a filigree of oxygen ions glowing faintly in the voids between galaxies. Dubbed the warm-hot intergalactic medium, this gas is 1,000,000 times less dense than the air we breathe, but so vast it could account for the missing baryons. The catch: even this discovery doesn't fully balance the books. Some of the gas is so hot, tens of millions of degrees, that it emits X-rays too faint for current telescopes to detect. Others speculate it might be hiding in cosmic filaments, those thread-like structures of dark matter that weave the universe's large-scale web. There's also the unsettling possibility that some baryons have been whipped into exotic forms by extreme physics near black holes or neutron stars, becoming effectively invisible to our instruments. What makes this puzzle so urgent is its implications. If we can't even find ordinary matter, how can we hope to understand dark matter or dark energy? The missing baryons are like a cosmic detective story, with every clue leading deeper into the universe's hidden architecture. New instruments like the upcoming Athena X-ray Observatory aim to map these ghostly reservoirs, shining a light on the darkest ledgers of the cosmos. Until then, the universe's accounting error remains one of its most persistent open cases, a reminder that even the stuff we think we know can vanish before our eyes. At the very edge of our galaxy, where the Milky Way's spiral arms should fade quietly into the void, something unnatural looms, a wall of energy so intense it baffled the very probes that discovered it. When NASA Voyager 1 and 2 spacecraft neared the boundary of our solar system, they didn't just encounter the expected drop in solar wind particles, they slammed into an invisible force field, a turbulent sea of high-energy particles crashing against the galactic shoreline like an invisible storm. Scientists call it the galactic barrier, and it's not just a boundary, it's a cosmic puzzle wrapped in radiation. For decades, researchers assumed the transition from solar system to interstellar space would be smooth, a gradual fading of the sun's influence. Instead, Voyager's instruments recorded something startling. A sharp spike in cosmic rays, a surge of particles accelerated to near light speeds, as if the probes had hit an electrified fence at 70,000 kilometers per hour. The intensity was unlike anything predicted, radiation levels 3 times higher than anything seen deeper in the galaxy, forming a diffuse but potent shield stretching at least 1.5 billion miles thick. What could possibly generate such a barrier? One theory points to the Milky Way's magnetic field, which might compress and amplify at the galaxy's edge, creating a kind of electromagnetic dam that traps high-energy particles. Imagine a river meeting the ocean where currents collide and churn into whitewater, except here, the currents are made of plasma and magnetic waves. Another possibility involves dark matter, the invisible scaffolding of the universe. Some models suggest dark matter particles could accumulate at galactic edges, their annihilation producing the very radiation Voyager detected. But the mystery only deepens when you consider scale. Our entire solar system is a speck compared to the Milky Way, yet this barrier appears to encircle the galaxy like a force field in a science fiction epic. If it's a natural phenomenon, why don't we see similar structures around other galaxies? Or perhaps we simply haven't looked closely enough. The barrier's existence forces us to reconsider how galaxies interact with the intergalactic medium, the thin, ionized gas that fills the voids between them. The most tantalizing clue comes from the barrier's uneven texture. Voyager's data revealed pockets of extreme turbulence within the barrier, regions where particle density fluctuated wildly, as if something were stirring the cosmic pot. Could this be evidence of unseen astrophysical processes, like shock waves from ancient supernova or the gravitational echoes of long-dead stars? Or is it a sign of something more exotic, a fingerprint of physics beyond the standard model? For now, the galactic barrier remains one of the least understood and most dramatic structures in our cosmic neighborhood. As newer probes like NASA Interstellar Mapping and Acceleration Probe prepare to study this frontier in greater detail, one thing is certain: the edge of our galaxy isn't a quiet frontier. It's a roaring, crackling borderland where the rules of space itself seem to twist and warp, daring us to rethink what we know about the boundaries of home. Black holes are supposed to be cosmic giants, lurking in the centers of galaxies or born from the explosive deaths of massive stars. But not this one. Just 1,500 light-years from Earth, in the constellation Monoceros, astronomers have discovered something that shouldn't exist. A black hole so small, so out of place, they've nicknamed it the Unicorn. At just 3 times the mass of our Sun, this pint-sized gravitational monster defies everything we thought we knew about how black holes form, and its very existence hints at a hidden population of these cosmic oddballs hiding in our galactic backyard. Most known black holes fall into 2 categories: stellar mass black holes, born from collapsing stars at least 20 times heavier than the Sun, or supermassive behemoths millions to billions of times the Sun's mass, anchoring the centers of galaxies. The Unicorn fits neither. It's part of a mysterious new class astronomers call mass gap black holes, objects too small to form through traditional stellar collapse, yet too dense to be neutron stars. Until now, they were purely theoretical. But the Unicorn isn't hiding in some distant galaxy. It's right here, orbiting a faint red giant star, its presence betrayed only by the way its gravity tugs the star into an odd, stretched-out orbit. Finding such a tiny black hole was like spotting a needle in a galaxy-sized haystack. Unlike larger black holes that announce themselves with blazing accretion disks or X-ray jets, the Unicorn is completely dark. Researchers only noticed it because its companion star wobbles unnaturally, as if pulled by an unseen dancer. Detailed measurements revealed the invisible culprit must be compact and incredibly dense, too massive to be a neutron star, yet smaller than any black hole ever confirmed. It's like discovering a planet-sized mountain. The laws of physics say it shouldn't stand, yet there it is. So how did the Unicorn form? One possibility is that it's the remnant of a rare, low-mass star that somehow bypassed the neutron star stage entirely, perhaps by forming in a dense stellar environment where interaction stripped away its outer layers prematurely. Another theory suggests it might be the result of two neutron stars merging, creating an object just heavy enough to collapse into a black hole but not massive enough to fit conventional models. There's even speculation that some mass-gap black holes could be primordial leftover relics from the universe's earliest moments, lurking undetected until now. What makes the unicorn truly remarkable is its proximity. If such tiny black holes are this close, how many more might be out there, invisible against the blackness of space? Current estimates suggest there could be hundreds of millions scattered across the Milky Way, a hidden archipelago of gravitational anomalies rewriting the rules of stellar evolution. Future telescopes like the Vera Rubin Observatory could uncover dozens more by spotting their subtle gravitational effects on neighboring stars. The unicorn isn't just a curiosity, it's a key to unlocking one of astrophysics' most persistent gaps in knowledge. Its existence forces us to reconsider how black holes are born, how they evolve, and whether the universe has been quietly hiding an entire family of these miniature monsters right under our noses. For now, this cosmic unicorn remains a beautiful enigma, grazing quietly in the stellar fields of Monoceros, daring us to rethink what we know about the darkest objects in the sky. Imagine if you woke up one morning to find footprints leading out of your bedroom except no one had walked there. That's the essence of dark matter, an invisible presence leaving gravitational tracks across the cosmos while stubbornly refusing to reveal itself. We know it's there because entire galaxies spin faster than they should, their outer stars whipping around as if gripped by unseen hands. Galaxy clusters bend light like cosmic magnifying glasses, their gravitational pull far exceeding what visible matter can account for. Even the universe's large-scale structure, with its vast web of filaments and voids, couldn't have formed without some invisible scaffolding holding it together. Yet after decades of searching, we still can't say what dark matter actually is. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed something bizarre about the Coma cluster. The galaxies within it were moving so fast that they should have flown apart, unless some hidden mass was gluing them together. He called it Dunkel Materie, dark matter, a placeholder for the inexplicable. Decades later, Vera Rubin's observations of spiral galaxies confirmed the anomaly. Stars at the edges of galaxies orbit just as quickly as those near the center, defying Newton's laws unless an unseen halo of matter surrounds them, its gravity propping up the stellar dance. So why can't we catch it? Scientists have turned entire mountains into detectors, like the ultra-sensitive instruments buried in Italy's Gran Sasso laboratory, waiting for dark matter particles to bump into atomic nuclei. Others have sent satellites like Fermi to scour the skies for gamma rays that might betray dark matter annihilations in space. Some theories suggest dark matter could be WIMP, weakly interacting massive particles that barely touch ordinary matter except through gravity. Others propose actions, hypothetical particles so lightweight they stream through planets like ghosts through walls. The plot thickens with recent observations that challenge even these ideas. The European Space Agency's Gaia spacecraft has mapped the motions of millions of stars, revealing subtle gravitational wrinkles that don't quite match standard dark matter models. Some galaxies, like Dragonfly 44, seem to be almost entirely dark matter, while others, like NGC 1052, appear to have none at all. These outliers hint that dark matter might be more complex than a single particle, perhaps a family of particles, or even a shadow universe with its own invisible physics. Then there's the radical possibility that we've been wrong all along. A minority of scientists argue that dark matter doesn't exist, that instead, gravity itself behaves differently at cosmic scales, a theory known as modified Newtonian dynamics. Yetman struggles to explain all the evidence, like the bullet clusters separated dark and visible matter after a galactic collision. The debate rages on, a testament to how profoundly this mystery unsettles our understanding of reality. For now, dark matter remains the universe's most pervasive secret, outweighing visible matter 5-1. It's the architect of cosmic structure, the unseen conductor of galaxies, and yet it slips through our detectors like a rumor. Every null result, every unexpected observation, forces us to rethink not just what dark matter is, but how deep the rabbit hole of the unknown truly goes. Until we catch it, this enigmatic substance will continue to rewrite the rules from the shadows, a ghost in the machinery of the cosmos. The universe is expanding, that much we know. But how fast it's expanding has become one of the most heated debates in modern cosmology, a discrepancy so stubborn it's been dubbed the Hubble tension. On one side, we have meticulous measurements of the cosmic microwave background, the faint afterglow of the Big Bang suggesting the universe is growing at about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova peg the number closer to 73. That tiny gap might not sound like much, but in the precise world of astrophysics, it's a screaming alarm bell. If both methods are correct, our understanding of the cosmos might be missing a fundamental piece. This isn't just academic quibbling. The Hubble constant, the rate at which the universe stretches, is the yardstick we use to measure everything from the age of the cosmos to the fate of galaxies. So when two gold standard techniques disagree, it's like checking the same distance with two rulers and getting different answers. The cosmic microwave background, mapped by the Planck satellite, reflects the universe's baby picture, extrapolating its current expansion from infancy. Meanwhile, observations of Cepheid variable stars and Type Ia supernova act as cosmic mile markers, measuring expansion directly in today's universe. Both methods have been refined for decades, yet the gap persists, growing more glaring with each new dataset. What's behind the mismatch? One tantalizing possibility is that the universe isn't playing by the rules we've written. The standard model of cosmology rests on pillars like dark energy and dark matter. But what if these are just approximations of something stranger? Some theorists propose an early burst of dark radiation, briefly turbocharged the young universe's expansion, throwing off Planck's predictions. Others suggest dark energy isn't constant but evolves over time, subtly altering the expansion rate in ways we haven't accounted for. There's even speculation about a dark fluid blending properties of dark matter and energy, or hidden interactions between known particles and shadowy counterparts. Then there's the wild card: our cosmic neighborhood might be weird. Local measurements could be skewed if we're sitting in a sparse bubble of matter, where gravity's weaker tug makes nearby space expand faster than average. But this explanation feels like a bandage. The void would need to be improbably large, and recent galaxy surveys haven't found evidence of such a structure. The Hubble tension isn't just a problem, it's an opportunity. Historically, discrepancies like this have led to breakthroughs, from dark energy's discovery to the realization that the universe is accelerating. With next-generation telescopes like the James Webb Space Telescope and the Vera Rubin Observatory set to deliver even sharper data, we might be on the cusp of uncovering new physics that rewrites the cosmic playbook. Until then, this tension remains a humbling reminder. The universe still holds cards it hasn't shown us, and the simplest answers aren't always the right ones. When a star dies, it's supposed to go out with a bang, a brilliant supernova that rips it apart in a final, violent act. But deep in the cosmos, some stars refuse to play by the rules. They're called Type Ix supernova, and they're the universe's ultimate cosmic cheaters. Stellar explosions so feeble, the star somehow survives. Astronomers call them zombie stars, not because they rise from the dead, but because they linger in a ghostly half-life, battered and burned yet still clinging to existence. These cosmic anomalies shouldn't exist, yet they're rewriting the book on how stars die. The first clue that something was different came in 2002, when astronomers spotted a supernova in the galaxy NGC 1309 that was oddly dim, just 1% the brightness of a typical stellar explosion. Instead of obliterating the star, it appeared to leave behind a mangled remnant, a white dwarf scorched but not destroyed. Since then, dozens more of these strange events have been catalogued, each following the same bizarre script: a weak explosion, a dim afterglow, and a star that refuses to die. What makes zombie stars so puzzling is their origin. Most type IX supernova occur in binary systems where a white dwarf, the dense core of a dead star, siphons material from a companion until it reaches a critical mass and detonates as a type Ia supernova. But in these cases, the explosion fizzles. One theory suggests the white dwarf only partially detonates, like a firecracker that sputters instead of exploding, leaving its core intact. Another idea posits that the companion star itself plays a role, perhaps absorbing some of the blast or destabilizing the explosion before it can fully destroy the white dwarf. Then there's the aftermath. Survivors of these failed supernova aren't just wounded, they're transformed. Observations suggest these zombie stars are left spinning rapidly, their surfaces scorched by the blast, and in some cases hurled across space at high speeds like shrapnel from a cosmic grenade. The most famous example, supernova 2008 Ha, left behind a white dwarf moving at nearly 6 million miles per hour, fast enough to escape its galaxy entirely. But the biggest question remains: why do some stars survive while others don't? The answer could lie in the delicate balance of physics at the moment of detonation. A slight asymmetry in the explosion, a fluctuation in the star's composition, or even the influence of magnetic fields might tip the scales between total destruction and a second chance. Some researchers speculate these events could be more common than we think, hidden in plain sight because their faint signatures blend into the cosmic background. For astronomers, zombie stars are more than just curiosities. They're a window into the messy, unpredictable ways stars meet their end. Every new discovery chips away at the neat categories we've built, reminding us that the universe thrives on exceptions. These stellar survivors force us to ask, if a star can cheat death, what else have we gotten wrong about the cosmos? Somewhere in the depths of the Milky Way, a world exists where the phrase, "diamonds are forever," takes on a cosmic significance. PSR J1719-1438b. This exotic planet, circling the corpse of a dead star, defies every expectation of what a world should be. Forget rocky surfaces or gaseous atmospheres. This is a planet quite literally made of diamond, a glittering sphere of crystallized carbon forged in the extreme furnace of a pulsar's wrath. The story begins with the planet's parent star, or rather, what's left of it. PSR J1719-1438 isn't just any stellar remnant. It's a pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse. Discovered in 2011, this pulsar's rhythmic radio pulses revealed a subtle wobble, betraying the presence of an orbiting companion. But when astronomers calculated its mass, slightly more than Jupiter's, and its composition, they realized this was no ordinary planet. The density was all wrong for gas or rock. Instead, the math pointed to something extraordinary, a world compressed into crystalline perfection, its carbon atoms locked into the rigid lattice of diamond. How does such a surreal world form? Picture this: a once massive star orbiting so close to its sun-like companion that it began siphoning off material, stripping its outer layers until only a helium-rich core remained. When the larger star eventually collapsed into a supernova, the explosion should have vaporized everything nearby. But in this case, the companion star, now reduced to a white dwarf, survived, only to be further crushed by the pulsar's gravity. Under unimaginable pressure, the white dwarf's carbon crystallized, leaving behind a diamond core the size of a planet. It's as if the universe took a star and squeezed it until it turned into jewelry. But here's what truly baffles scientists: this diamond planet shouldn't exist at all. Current planetary formation theories struggle to explain how such a dense, carbon-rich world could form in the chaotic aftermath of a supernova. Pulsar planets are already rare, only a handful have ever been confirmed. and none match this one's bizarre properties. The intense radiation blasting from the pulsar should have evaporated any nearby object long ago, yet this diamond world endures, locked in an orbit so tight a year lasts just 2 hours. What secrets does this cosmic gem hold? For one, it challenges our assumptions about the diversity of planets. If diamond worlds can form around pulsars, might there be other exotic variants planets made of sapphire or even metallic crystals? The discovery also raises eerie questions about the fate of solar systems when stars die. Most models assume violent stellar deaths obliterate their planets, but PSRJ 1719-1438b proves some worlds can survive transformed into something entirely new. For now, this diamond planet remains a glittering enigma, a testament to the universe's capacity for both destruction and creation. It's a world born from catastrophe, forged in extremes, and lingering as a shimmering relic of cosmic alchemy. And as long as it spins in the pulsar's deadly glow, it will keep challenging our understanding of how planets and precious stones are made. In the quiet darkness between galaxies, where radio telescopes usually pick up only faint whispers of cosmic static, astronomers stumbled upon something that shouldn't be there. Enormous, perfect circles glowing in radio waves like cosmic smoke rings etched across the sky. Discovered in 2020, these odd radio circles, ORCs for short, aren't just strange, they're impossible. Stretching hundreds of thousands of light years across, each one dwarfs entire galaxies, yet they emit no visible light, no X-rays, no infrared, just eerie, looping radio emissions with no obvious source. And the most baffling part, we still don't know what they are. The first ORC blinked into existence on telescope data like a fingerprint on a blank page. Researchers scanning the sky for faint radio signals nearly dismissed it as an artifact, a glitch in the machinery, but then they found another and another. By 2023, 6 of these enigmatic rings had been catalogued, each one a ghostly halo floating in deep space, far from any known galaxy or star-forming region. Their symmetry is uncanny near perfect circles, as if someone or something drew them with a cosmic compass. And they're old, their light taking hundreds of millions of years to reach us, meaning whatever created them did so in a universe very different from our own. Theories about their origins range from the plausible to the borderline surreal. One leading idea suggests they're shockwaves from cataclysmic events, perhaps the aftermath of supermassive black holes colliding, sending ripples through intergalactic gas like a stone dropped in a pond. The energy released in such a collision could theoretically sculpt these vast rings, but there's a catch. No such collisions have been detected in the regions where ORCs loom. Another proposal ties them to starburst galaxies, where frenetic star formation might drive massive galactic winds, inflating bubble-like structures visible only in radio waves. Yet ORCs don't always appear near active galaxies, leaving this explanation on shaky ground. Then there's the wild card. ORCs might be the throats of wormholes. Some theorists speculate these circles could be the mouths of space-time tunnels, their intense magnetic fields accelerating particles into the telltale radio glow. It's a radical idea, but not impossible. Einstein's equations allow for wormholes, even if we've never found one. Others whisper about extraterrestrial engineering, though most scientists dismiss this as wishful thinking. The real frustration lies in their elusiveness. ORCs don't emit at other wavelengths, making them nearly invisible to most telescopes. They're like cosmic neon signs that only glow in one color, a color we barely know how to study. New observatories like the Square Kilometre Array, set to come online in the next decade, could finally crack the code, peering into these rings with unprecedented sensitivity. For now, ORCs remain one of the universe's most arresting puzzles. They're not explosions, they're not galaxies, and they're not echoes of the Big Bang. They're something else entirely, a reminder that even in an age of precision astronomy, the cosmos can still throw a perfect circle at us and leave us staring, slack-jawed, into the static. Every new detection peels back another layer of mystery, but until we understand what's casting these vast radio wave shadows, they'll keep haunting the edges of our maps, whispering that there's so much more to space than we've dared to imagine. The CMB cold spot isn't just a quirky blip in the universe's oldest light. It's a cosmic bruise, a patch of sky so unnaturally cold it feels like the universe itself is holding its breath. Nestled in the constellation Eridanus, this icy void spans nearly 1.8 billion light-years, a staggering expanse where the afterglow of the Big Bang dips in temperature like a phantom finger pressed against the fabric of space-time. When scientists first mapped the cosmic microwave background with satellites like WMAP and Planck, they expected minor fluctuations, tiny wrinkles in the universe's baby picture. But the cold spot stood out like a frozen wound, its temperature plummeting 20 times farther than any standard model could explain. What makes this anomaly so unsettling isn't just its size, it's the fact that it shouldn't exist. According to our best theories, the early universe was a seething, chaotic place, but its imperfections should have smoothed out into gentle, random variations. A cold spot this vast and deep defies the odds, like rolling a dice 1,000,000 times and always landing on zero. One leading explanation, a supervoid, an unfathomably empty region of space where galaxies and matter are eerily scarce. As light travels through such a void, it loses energy, stretching into cooler wavelengths like sound fading in a tunnel. But here's the catch: the void needed to explain the cold spot would have to be impossibly large and empty, a cosmic vacuum cleaner sucking up matter with a voracity that defies gravity's pull. Then there's the far more radical possibility. The cold spot might be a scar from a collision with another universe. Imagine our cosmos as one bubble in a frothing multiverse, where neighboring universes occasionally bump against each other. Such a collision could have siphoned energy from our spacetime, leaving behind a frigid imprint like a tire mark on wet pavement. The idea isn't as far-fetched as it sounds. Cosmic inflation theories already suggest our universe may be one of many, and the cold spot's sharp edges align eerily with what such a collision might look like. But the plot thickens when you examine the void itself. Surveys like the Dark Energy Survey have scoured the cold spot's territory, expecting to find a near-total absence of galaxies. Instead, they've uncovered a sparse but not entirely empty region, like a desert with a few scattered oases, not the barren wasteland the cold spot's chill demands. This mismatch has led some to propose even wilder explanations, like cosmic textures, defects in spacetime itself, leftover kinks from the universe's violent birth. These hypothetical wrinkles would warp light and matter in ways that mimic a void without requiring one to actually exist. The cold spot's resilience as a mystery speaks to the limits of our cosmic maps. Every new observation peels back another layer, only to reveal deeper questions. Could it be a statistical fluke, a cosmic mirage amplified by our limited vantage point? Or is it a genuine crack in our understanding of reality, a signpost pointing to physics beyond the standard model? For now, it lingers like a whisper at the edge of our data, a cold reminder that the universe's oldest light still holds secrets we're only beginning to decode. Whether it's a window into the multiverse or simply a shadow cast by something we've yet to name, the cold spot challenges us to rethink not just our place in the cosmos, but the very nature of reality itself. The universe keeps meticulous records except when it comes to lithium. According to the pristine equations of Big Bang nucleosynthesis, the same process that forged hydrogen and helium in the fiery first minutes of creation should have left behind a specific amount of lithium-7, about 1 atom for every 10 billion hydrogen atoms. Yet when astronomers peer into the ancient stars of our galaxy, the ones that have preserved their primordial chemistry like cosmic time capsules, they find a glaring discrepancy. The lithium is missing, not just a little, up to 3 times less than the models predict. This cosmic accounting error has persisted for decades, a nagging gap between theory and observation that threatens to upend our understanding of the universe's earliest moments. The mystery begins with the Big Bang's alchemy. In those first fleeting minutes, temperatures and densities were so extreme that atomic nuclei could fuse directly from raw protons and neutrons, a process called nucleosynthesis. The math behind these reactions is exquisitely precise, accurately predicting the abundances of hydrogen, helium, and their isotopes except for that stubborn lithium shortfall. It's as if the universe baked a perfect cosmic cake, but someone sneaked into the kitchen and stole a handful of raisins before serving it. Where could the lithium have gone? One possibility is that stars themselves are the culprits. Ancient stars, born from nearly pure Big Bang material, might have processed lithium in ways we don't yet understand. Some theories suggest convection in these stars could drag lithium down to scorching inner layers, where it's destroyed in nuclear reactions. Others propose that lithium gets trapped in stellar atmospheres, hidden beneath layers of other elements like a needle in a haystack. But even these explanations fall short. Detailed stellar models can't account for the full deficit, and younger stars, which shouldn't have altered their lithium much, still show the same shortage. Then there's the wild card, new physics. What if the early universe wasn't as uniform as we think? Tiny variations in temperature or density during nucleosynthesis could have skewed lithium production, or perhaps unknown particles interacted with nuclei in ways that suppressed its formation. Some theorists even speculate about primordial black holes, microscopic relics of the Big Bang, swallowing lithium-rich regions before stars could form. Others point to cosmic rays, which can break apart lithium nuclei in interstellar space, though this seems insufficient to explain the scale of the problem. The most tantalizing clue comes from the few stars that do show lithium levels matching predictions. These rare exceptions are often metal-poor giants, suggesting that lithium destruction or depletion isn't universal. If we can figure out why these stars preserved their lithium while others didn't, we might crack the case. New telescopes, like the James Webb Space Telescope, are now examining these outliers with unprecedented precision, searching for patterns in their chemistry or environments that could reveal the missing piece of the puzzle. For now, the lithium problem remains one of cosmology's quietest but most persistent embarrassments. It's a reminder that even our most successful theories have cracks, and that the universe's earliest moments might still hold secrets we've yet to uncover. Every atom of lithium in the cosmos carries a fingerprint of creation, and the fact that so many are missing suggests there's a chapter in the story of the Big Bang we're only beginning to read. From the ghostly whispers of the WOW signal to the immense, silent void of the Boötes void, these 25 cosmic anomalies show us just how little we truly understand about the universe. Each one defies expectations, challenges our models, and forces us to reconsider what we thought we knew. Whether it's the eerie symmetry of the Red Rectangle Nebula, the unsettling pull of dark flow, or the unanswered riddle of the missing baryons, these mysteries remind us that reality is far stranger, far more unpredictable than science fiction could ever invent. But here's the beautiful part. These aren't just gaps in our knowledge, they're invitations. Every unexplained signal, every impossible structure is a door waiting to be opened, a question begging to be explored. The universe isn't just a collection of facts, it's a dynamic, evolving puzzle where the pieces keep changing shape. And that's what makes astronomy so thrilling, because just when we think we've got it all figured out, the cosmos throws another curveball, humbling us and inspiring us in equal measure. So where do we go from here? The search for answers is never over. If you're hungry for more mysteries, dive into the enigma of dark energy, the paradox of quantum entanglement, or the unsolved origins of fast radio bursts. Check out our videos on the Fermi Paradox or the holographic universe theory, And most importantly, stay curious. The next great cosmic revelation might be hiding in data we've already collected, waiting for someone to connect the dots. Now it's your turn. Which of these anomalies fascinates you the most? Do you think Tabby's star is surrounded by alien megastructures, or is there a simpler explanation? Could the Eridanus supervoid really be a window into another universe? Drop your thoughts in the comments below, because the best thing about these cosmic puzzles is that they belong to all of us. The universe is a shared mystery, and every perspective brings us one step closer to understanding it. So keep looking up, keep questioning, and remember, somewhere out there, in the vast darkness between the stars, the next great anomaly is waiting to be discovered. All we have to do is pay attention.